remember you sent me email. I respond you back. You didn't get my email back?
No. So I ended up asking you questions about graduation, and you did send me back an email, but I do have a couple of questions on homework 3
Okay.
for today.
I thought it was in this case. It was. I remember one person asked me a question about homework, and so what was the first homework? It was problem
It was problem
2.3.
2.3. Yeah.
Okay.
Mhm.
And what's
So the first one, when it's asking about the microstates, is that asking about how many outcomes each microstate has, or how many microstates there are in total?
how many microstates are in total? For
Okay.
example, if you have a one coin, how many microstates you can have? Two. Yeah.
Yeah.
If you have a two coins, how many microstates you can have?
4.
Four. If you have a three coins, how many you have?
You would have 8.
Eight, and so on.
Okay.
In this case, you can do it.
Yeah. And then the second part, it says how many ways are there of getting exactly 25 heads and tails? Would that? I'm not really sure how to interpret that question.
It implies that you have a situation where you have so you have 50 positions where you can have a heads, and you have a 20. So you have a 50 times when you done experiments, yeah. So it's a 50 of them, okay. And you need to put in 25 times heads, yeah.
Yeah.
So in how many ways you can arrange heads in these 50 options?
Okay.
That's what does it mean.
Okay. Those were the only questions I had for this.
Okay. Okay, great. In this case, it's I see people arrived, so we can start our lecture. So I will go very briefly, and we can discuss it after group meeting, or after, sorry, not group meeting, after the class. Sorry, let me just raise the camera just a tiny bit higher, just too low. Okay, so it's now it's set higher. Perfect. Okay. So last time, remember we have a question about Heisenberg uncertainty principle. Okay, so I will go over this very, very quickly. I will make a reference to where it is discussed in more in details, and we can discuss it more after the class, okay? So last time when we did derivation, we discussed that we can apply simplified, like Heisenberg uncertainty principle, Heisenberg uncertainty principle, from last, in general, you know that is delta P times delta X is bigger or equal than H bar over 2, yeah? And this is what you used to see. And that's best case scenario, yeah? H bar over 2. Like it's when you have absolutely perfect measurements, and this is how you can accurately measure something, okay? And in a book, and what we derive a view and use it, we use it so saying that delta P times delta X is roughly is equal to H. And so if you look H bar over 2, it's equal to H over 4 pi. So, and here's become a question, why do we use this one? So in the book, they talk about it in appendix A. You can look in it in appendix A. So it's a page 364 to 366. And in general, what it's explaining, it's when we're talking about position, we sort of try to divide the space on the sub areas where particle could locate, yeah? So we can talk about use a model of wave packets. So we have wave packets where something could locate, yeah? We have a wave packets. And and we discuss it, we have a position of X and P with uncertainty delta X and delta PX, okay? And what we say, let's assume that our position accuracy for one particle is lambda. So we accurately measuring where something locating with up to 1 lambda. So delta x is roughly equal to lambda. Okay, so the size of one wave packet is approximately lambda. In this case, we can say that our accuracy to measure momentum is roughly equal to momentum itself, and then we can apply Lagrange equation, which is lambda is equal to h over p, and we can write down that px is equal to h over lambda, which is roughly equal to h over delta x. Okay, and from here we can do that. So idea is, yes, Heisenberg uncertainty principle is correct for that. That's very like sort of in the best possible scenarios. Usually it's much higher delta p times delta x. And in our case, we're talking about sort of closed environment, and we're discussing how many places so we can divide space on what kind of subspaces. So we can talking about concept of wave packets, sort of areas where something could locate. We divide in sub areas. That's why we apply the similar methods which explains in the back there, and we assume that, let's say, something have a volume uncertainty lambda. For example, in this case, we can calculate what will be uncertainty for the momentum. Okay, so I'm done for that point. You can look in Appendix A, and I could discuss with you more after the class. Okay, clear? Okay, so as I promised, I went back for this, and sorry at that time you put me in a spot, because I agree with you. It was a little bit confusing why I did this step in the book. But what we did with you after that, we find out the multiplicity for one molecule is volume times area of momentum space divided by h cube. This is for one molecule. Okay, and if we have two molecules, we have it as v over h cube square times area of momentum space and we need to multiply by 1/2, which is comes from where, guys? Because we have indistinguished particles, yeah, indistinguished particles, and we need to take into account that we can interchange them. And finally, last time we come up with a formula for n particles, for multiplicity of n, and we derive that it's equal to 1 for n large. It's 1 over n factorial, so we take into account that particles are indistinguishable. Vn over h free n 2m u pi times on the power 3.5 divided by 3n over 2 factorial. Okay, and this is what we did last time. Okay. Okay, now let's move to next section. This is where we stopped last time. So now we'll move to, this just was a review, guys. We're going to discuss the last point here, number 6, interaction of ideal gas. Okay. Number 6. Okay, is it number 6 then? With my, yeah, right notation. Okay, so let's talk about interaction of ideal gas. So let's have before we did one gas and we find out what is the multiplicity. Now we have two gases. We have a large system isolated from environment. We have double walls, and here we sort of separated into chambers. One of them have a volume VA, another have a volume VB. one of them has energy UA, another one have energy UB, and another one, but they all have the same number of particles. For right now, we have N and N. So in our case, A and A is equal and B is equal to N. So we have a system, two ideal gases separated by partition, okay, which allows energy flow. So two gases separated, separated by partition. And what if we can do? We can allow energy flow. Okay. But molecules cannot go from one system to another, but energy could go. Okay. So in this case, let's find what is the multiplicity of this system. What is multiplicity of the system? So in this case, we can use this formula here. Okay, and we can do that it's multiplicity A times multiplicity of B. And what we got here, you know what, we did this formula, and then last time we derived a shorter formula where we use a notation, which we can simplify it. We can write it down as f of n times v in the power n times u in the power of 3n over 2. Okay, this is what we did last time. Sorry, and we where f of n is equal to 2m pi in the power of 3n over 2 divided by n factorial h in the power of 3n over 2 factorial. Okay, so we'll use this formula just to make it simpler and easy to work with. So we have same number of particles, so f of n is the same for both of them. So we get f of n squared. Then we have a volume A in the power of n, volume B in the power of n, and our energy UA and UB in the power of 3n over 2. Okay. So you can see that we know that, guys, that what is the total energy of the system? Total energy is equal UA plus UB. And what is the total volume? Is equal volume A plus volume B, which we can write down here U and here is V. Yeah. So if we use that, we can slightly rewrite this formula for multiplicity. We can write that in terms of U and V and what happened in one of the volumes. So we can write that the U total is equal to f of n squared. And this one will keep VA, but VB will write as V minus VA. So we'll have it VA, V minus VA in the power of n. And the similar we'll do with UB. We'll have UA and U minus UA and everything in the power of 3n over 2. Okay. So now we have the function for multiplicity. When do we have the maximum of this multiplicity? It's the same as when we have all the time, and we can see this clearly. We have a maximum when VA is equal 1/2 of V. Yeah, it's the same story as we see before because it's a symmetrical function. So we have a sharp peak when VA is equal VB is equal V over 2, and when UA is equal UB is equal to U over 2. And you can see it's a two sets of coordinates. We have like two-dimensional peak, yeah? So if we want to plot it down, we sort of have a thing here, our volume A, and this is our U of A. So we sort of have our peak in two dimension, okay? Does it make sense? So we have now multiple parameters, and we have a peak when volumes is and energy divided equally between two ideal gases. Again, that's a situation when we have a same amount of molecules, and A is equal to NB. Okay. So now we can find what is V maximum in this, what is the peak value, what is this maximum value here. We know that this is a value, so we can apply here, and we can get that the maximum value is equal f of n square v over 2 in the power of 2n u over 2 in the power of 3n. And this is our peak and our width of the peak. Width for the peak, it will be in the same story as what we have, it same as for Einstein solid, and we get that width will be equal to u over square root of 3n over 2 and v over square root of n. Oops, sorry. And this peak has become narrow. If n is increases, in this case, our peak become narrow. And increase, peak become sharper. Okay. So idea is the same. We apply this, we have ideal gas. We just remember, if you have find the multiplicity of one gas multiplies by multiplicity of another gas. We apply formula. Then we look in when we have a peak. Here again we have a symmetrical case. If it will not be symmetrical, for example, if we have here not symmetric amount of gases, maybe in this case it will be shifted. And but it's a peak here, and it's a function of n. And obviously, as n become higher, this peak become narrow and narrow. It implies that what we discussed, guys, only few cases near the equilibrium could exist. If you go quite far away, you couldn't get it. And how we get this peak, the value of the peaks, guys? Remember last time we get Einstein formulas for solids. Let me see if I have a note from the previous classes. Last time, guys, we derived it, and if you remember when we did this, we made this in this form for Einstein solids, and we managed to find the function for the width, and we showed that it's the same as Gaussian. It's exactly the same story what we did last time. Look in our last week lecture. Okay. Now let's quickly look an example. Let's look an example of we have a chamber and we want to find what is the probability to have all gas in one side of the chamber. Find probability to have all gas, all particles in one side. So this is what we want to do. Okay. So what we can look at it, we can look at the situation that our volume become half of the volume, yeah? So we want to compare situation where we have one volume, and now we're looking in the half of the volume. So our multiplicity for volume is f of n, v in the power of n, u in the power of 3n over 2. Sorry, 3n over 2. And now we are going to half of the volume, so it is equal to of sorry, this is volume and this is of volume over 2. It's equal to f of n, v over 2 in the power of n, u 3n over 2. Okay. So if we'll take the ratio of them, we can see that our multiplicity reduced by 2 in the power of n. Yeah. So our multiplicity reduced by 2 in the power of n. So the probability is 1 over 2 in the power of n. That's the probability of having gas in one side. Questions? Guys, questions?
So it's pretty much impossible to have all the gas in one side.
Yeah. And that it's randomly by itself end up to be there. Okay. That's the idea. We can make some kind of work on it, and we'll discuss of the situation, what it caused, anything like to make a change by itself. It will the possibility of being on one side is almost impossible. Okay, now could I remove this paper, or you want me to keep it a little bit here on the side? Let's talk about next topic. Let's talk about entropy. Okay, entropy. So we'll talk about second law of thermodynamics. What is the second law of thermodynamics said? Second law of thermodynamics. Okay. It said that any large system in equilibrium will be found in the macro state with the greatest multiplicity, aside from fluctuation, which are small. Yeah. So it will like it's in the greatest multiplicity. So any large system in equilibrium will be found in the macro state with the greatest multiplicity. Okay. Aside from a fluctuation which are small. Aside of small fluctuation. Okay. And multiplicity tends to increase. Okay. Okay. So now that's what we know about second law of thermodynamics. Now let's introduce entropy and see what's going on in terms of entropy. So our number 1 subsection here will be definition. Okay. So how we'll define the entropy? It is defined as letter S. large letter S, and it's equal K logarithm of multiplicity. Okay. And well, as we study the entropy, it will help you to explain why we have flow energy for the cycle and how everything is like how the energy flows. So what is the entropy? Entropy is logarithm of the number of ways of arranging things in the system. So we have a system and we have a way how we can arrange it, and a number of ways, and it's logarithm of number of ways how we can arrange something. Okay, so let's look at an example. Yeah.
Can I ask something really quickly? That
Sure.
K is the same Boltzmann constant that
Yes.
we always use? Okay.
Yes, thank you very much. Yes, K is our famous Boltzmann constant. Yes. So let's look at an example when we have a large Einstein solids. Guys, do you remember, who could remind me what is Einstein solids? What's special about it? So we can have number of oscillators and we can give a number of units, and there is no limits how much of energy could be in each of the oscillator, yeah? It's the same as we have number of people and we have a changes, and there is no limits how many changes one person could hold, okay? So we have an oscillators, just to make sure that you remember, because it's something which we use all the time, Einstein solids, and I don't think you ever see this terminology before that, yeah? You never heard it before. So I'm just to make sure that you're aware of it. It's the same example of people in a room and the changes, and you can have infinite amount of changes. And oscillators, and we have Q units of energy. Okay, and we look in situation when so n is large, and we look in situation then we have significantly more energy or changes than oscillators. Okay, so in this case we discussed that our multiplicity is equal, and we derived it last time, is equal E of Q over N, where E is our like 2.7, yeah, E. Everything in the power of N. And from here, in this case, we can find our entropy very simply. It's equal to K logarithm of EQ over N in the power of N. Yeah. So we can put N outside, and we can get it equal to logarithm of Q over N plus 1. Okay. So what we can see for this one case, if Q increase, if we increase more energies, what happened with entropy? Will it increase or decrease?
Increase.
Increase. If N increase, what happened with entropy? Look carefully.
Decrease.
Increase too, because we also have it on top of them here. So that's why I said carefully. I know it was a tricky one. So no matter, we increase number of energy, we increase number of oscillators, we increase number of possibility what happened, and entropy increase. Okay. So to increase entropy, but I'm glad that you after your try, even if you're not sure, it's good. I prefer that instead of me just like a blah 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 all the time.
I'll try.
So let's look what we can do to increase entropy. We can add particles. Okay. We can add energy. Okay. But also what we can do, we can expand the space. So if we have more space, in this case, there is more places where something could locate, yeah? So we can expand space, expand to larger space. So we increase number of multiplicity, so we increase entropy. We can break larger molecules, yeah? So if we have large molecules, and now we break up, and now we have more particles, yeah? Break large molecules. And we mix together substances. So in all of these cases, what we do, we increase total number of possible arrangements, yeah? Number of possible arrangements. Okay? What does oh, I read some comment, but he already person figured it out. Okay. I see that people have a couple videos in front of me, so I could see if somebody writing, I'm making a pause. Okay, so let's look how we can define entropy in another way. Other way to define entropy. Okay, other way to define entropy. So in statistical mechanics, which part of this course here, we define concept of entropy entropy holds behind that concept of order and disorder of the system. Okay, how something order or how it's become more disordered. Okay, so in statistical mechanics, entropy concept is related to order and disorder. Order and disorder. Of a system. Okay. So entropy represents disorder or randomness. Okay. Entropy represent disorder or randomness. Okay. So because if we have something it's in order, we don't need much information to explain, but as we need to provide additional explanation of what happened with the system, sort of its entropy increase. Okay. Need more additional information to specify the exact physical state of the system. Okay, so entropy related to disorder or randomness, and sort of you can look on it as something is not ordered. We need more information to explain what is going on. So if you look in your house and if everything is organized, it's very easy. But let's say you're sending your friend to find out or ask you, oh, could you please bring me my homework? And they come to the house in complete disorder. And you need to specify, oh, you know what? It's below the bed in the box which says shoes wrapped up in a candy wraps. And there's my homework. So you see how much more you need to explain if something is disorder. So, I know it's not exactly, but at least you give me a feeling. Okay, let's move to next subsection. Okay, remove this paper. Let's talk about interaction of two systems. Interaction of two systems. Okay. So we will discuss about properties of entropy. Okay. So let's have a composite system. So we have system consists of A and B. We have so system. We have composite system which has multiple things. Yeah. And let's have it A and B. Okay. So in this case, let's look what happened with its entropy. So entropy total is equal K logarithm of multiplicity total. Okay. And we discussed that multiplicity total is equal to multiplicity of A times multiplicity of B. Okay. And this one could be written as K logarithm of A plus K logarithm of B. So you can see that we can define that total entropy is equal to entropy of A plus entropy of B. When you see this type of simple equations, like duh, it's obvious, but it's not necessary. Sometimes they have much more complicated, yeah? But for entropy, and as we add another object to the system, we just add this entropy. So total entropy is the sum of its parts. Okay. But it's very important. We are assuming that macro states of system A and B haven't been defined separately. Or if they are not defined separately, if they interact with each other, in this case, they will share microstates together, yeah? So it's very important that we assume that macrostate of system A and B have been defined separately. Okay. So now if there is a system A and B and they could interact with each other, in this case, what will happen? It will be some fluctuation in time, yeah? So if a system, just quick note for you, can interact, in this case, we have a fluctuation in time. Okay. And in this case, we need to look on total multiplicity on all macrostates in time, yeah? So in this case, need to look for multiplicity total on all macrostates. in time. Okay, and in this case, our entropy total will be changed in time, yeah, which makes sense, yeah. So if our system interacts, our multiplicity will be changing slightly in time, and in this case, our entropy will be changing in time. But what we know, if our system A and B are in equilibrium or in most likely microstates, in this case, all this fluctuation is small, and we'll get almost the same entropy. Yeah. So obviously, if it's far away from entropy, from equilibrium, in this case, you have some stronger fluctuation. But if it's sort of in regular environment, it's already come down. In this case, all this fluctuation is small. So if A and B systems in most likely microstate, in this case, fluctuations are small, and in this case, what we get almost same entropy. Okay, so let me put like that. Okay. So far, so good. I hope it does sort of basic concepts. So I hope it's all clear. We're just defining. And guys, you heard about entropy before, yeah? Could you please tell me yes or no if you heard about entropy before and you use entropy? I assume that everyone heard about it, but I just want to know if somebody never heard about entropy.
Yeah, I've heard of it before.
Okay. So pretty much everyone heard about entropy. Okay, I just was curious. So I'm just going to go over it quickly, and we will use it obviously in much more complicated way. I'm not sure you calculate in terms of microstates, yeah? You never needed to use a probability. Here you'll need to use all these tricks. Okay, so let's talk about second law of thermodynamics in terms of entropy. Okay. Could I remove this paper? Top one? Assume you okay, keep it like that. So any large system in equilibrium one more time. Any large system in equilibrium will be found in the macrostate with the greatest entropy. So that's pretty much second law of thermodynamics, aside from fluctuations. And the entropy tends to increase. So any large system in equilibrium will be found in the macrostate with the greatest entropy. Okay, entropy, aside from fluctuation. I always need to mention it. Aside from small fluctuation. Okay, and entropy tends to increase. So if we have a system not in equilibrium, what will happen in this case? It will go with a situation to get reaching entropy, which implies that entropy will increase. Okay. question for you guys, and I will want your responses. Is it possible to decrease entropy?
With outside work, maybe?
Explain, how could you increase, or so what is the entropy and what does it mean to decrease entropy and how we can do it? I'm waiting.
So entropy is the loss of energy from one system to another, correct?
Or if we have one system has entropy, yeah? We have something which has an entropy. What is it? We said it could be in terms of order, yeah? Something it's entropy is sort of related to disorder of a system. So what does it mean if we want to decrease this entropy? We make it more ordered, yeah? Could we decrease entropy? Could we make system more ordered? For example, you come to we discussed the example that your room, which has completely, not your room, your friend room, you're all perfect, sorry. All my students completely perfect, they have perfect rooms. You some strange friend who have completely disordered room with full house in it, yeah? Could you arrange his room and make an order in his room?
Probably not to their condition.
But could you come in and do this? Could you arrange and make it everything in order? Or his parents came in, or her parents, yes?
Yeah, the relative part is what I'm, like what's ordered to me would be different to someone else. But I guess you could, technically speaking, come in and do the work for them.
Exactly. So you can come in like you have completely all dirty dishes. Yes, they're completely in disorder. And somebody, your mom come in and wash all your dishes and put them all in place and she put in everything in order. So you can do that. But what does it imply? That you by yourself, let's say, not you, I'm talking about your friend by himself, cannot do clean dishes and put them all in places. So somebody else come in and do the work, exactly use all the right words and arrange everything to make it all in order, yeah? So what it's done, we use extra energy from environment, from outside, not in the system of this house. The system in the house is completely disordered, but something comes in, bring this energy, work, and make it order, yeah? But let's say that your friend's mom, she used the energy, yes? So yes, we make order in one place, but and in this case we decrease the entropy. But because your friend's mom did work, she produced entropy. Okay. Does it make sense now? So the answer is yes, we can decrease entropy of the system, but to do that we need to provide work from environments. And if you took everything in account, overall you increase the entropy. Okay. Clear? Okay. Glad with dirty dishes.
Can you repeat that one more time? I'm sorry, I'm getting a little bit confused.
Oh, absolutely. So, example of the dishes and entropy. You have disorder, yes? You can make system more in order, like in disorder, it means high level of entropy. You can, to order it out, you need somebody else will come in from environment, yes? Come in and put everything in order. And in this case, the entropy goes down. So the more ordered, the entropy is low. But to do this work of the environment, we will, to this decrease this entropy, we'll also need to create more entropy, like mom will need to come in and do this work. So she used her entropy to create it, okay?
Okay, thank you.
So overall, and then we'll discuss this later, the whole entropy of the world always stay the same or increase. And this is what we'll show later. So let me just quickly write down, we can decrease, okay? so can use energy from environment, yeah. Okay. And but overall entropy of the system plus environment will increase, yeah, or stay the same. Okay, so we'll show later that delta S will be big or equals show later. We'll walk about this. Okay. Okay. Now let's move on. Let's talk about entropy of ideal gas. Okay. Okay. So let's talk about what is the multiplicity of ideal gas with n particle. So we have ideal gas, n particles. And in this case, multiplicity is equal to 1 over n factorial, v in the power of n divided by h in the power of 3n, pi in the power of 3n over 2 divided by 3n over 2 factorial times square root of 2mu in the power of 3n. Okay, and here's n large, yeah, as well, just in case. So where this comes to 1 over n factorials? What is represented? It's come from that particles are indistinguishable, okay? And while we'll talk about this, because later we'll make an effort. So let me make sure that you understand this has come from indistinguishable particles here. And these parts, yeah, come from position, momentum, volume. Yeah. So this is our multiplicity. So now we can find what is entropy, yeah? It's k logarithm of n. Oh, by the way, guys, I'm just curious, did anyone even looked in math sheets with practice of simple math to try now? I put it for you online to have just simple math.
I saw it, but I haven't done it yet.
I was just curious if, like, guys, if you feel comfortable, you find it just for you. It's very simple, like, because you can see we will use a lot of logarithms back and forth, and I'm expecting that you'll know, but sometimes you may have not a good high school, so it's a good if you need a practice. I had like a 50 pages, which I did once for a girl of different math equations. She took in parallel with my class just to increase her math level. So I hope you don't need it. But it's better to accept it than sometimes you don't know something and fix it instead of feel sorry for yourself and fail the class. Okay, so let's move on. Sorry, entropy. So let's plug in this formula. So we'll do some rearrangement of it. We'll put it k logarithm of 1 over n factorial 3n over 2 factorial plus logarithm of v in the power of n pi in the power of 3n over 2 divided by h in the power of 3n square root of 2mu in the power of 3n. Okay. And we will use Stirling approximation. Which said that logarithm of n factorial is roughly is equal to n logarithm of n minus n. Okay. And we can rewrite it and get that entropy is equal k. And here, guys, make sure you're not losing any minuses, because where is this n factorial? It's in the bottom, so it will have a minus, yeah? And then when we'll go here, there is another n logarithm n, and here's a minus. So make sure you keep all your signs, okay? So let's first make it simpler. We'll do step by step. Let's write it like that. Minus logarithm of n factorial minus logarithm of 3n over 2 factorial. I'll just simplify it. And we can write it down as logarithm of v pi 3 over half 2m u in the power of 3 half over h cubed and everything in the power of n. And then I will use a Stirling approximation. In this case, we'll have less chance to lose a minus. Minus nln plus n minus 3n over 2 times logarithm of 3n over 2 plus 3n over 2. Here we can remove n in front of logarithms. Sorry, it's not, it should be here plus, sorry, plus n logarithm of vp 3.5 2m u 3 half h. Okay. Sorry. Let me just write it clearly. Could you read my notation, guys? Clear? Okay. Okay. So we've done that. Now we can remove n outside. You can see everything has n and outside and group it together. So we can get kn. And then we get here minus logarithm of n times 3n over 2 in the power of 3 half. Does that make sense? So I remove n's, and here logarithm of n, so we get n, and here we have 3n over 2, and this n was going out, but this is 3 half, goes to the power. Okay? Plus 5 half plus logarithm of v 2m pi u over h square in the power of 3 half. Okay. And the last thing, we can combine these logarithms together and we can get it's equal kn. And this is our the final formula. You know, let's me do the steps. Kn 5 over 2 plus logarithm of v 2m pi u in the power of 3 half divided by h in the power of 3 times 2 in the power of 3 half divided by n and 3n in the power of 3 half. So you need to just do very careful job that you'll not lose anything. So we combine this together. Okay.
Is that h cubed under that first one?
It's h cubed, yes.
Thank you.
Rewrite it that differently, and I will rewrite it again sort of combined together. So you can see here 2 and 2, so we can combine together. And and here's a cube. So what we can do, we can write in a very nice formula for entropy, and it will look like Kn logarithm of V over n, and here 4m pi u over 3h square n in the power 3 half plus 5/2. Okay, and this equation is for entropy of ideal gas. And this formula called Sackur-Tetrode equation. Sackur-Tetrode equation. Okay. Now let's look at an example. Let's look at an example. Let's look at an example that we have ideal gas and its expanse. Yeah. Okay. And we have a so we have expanding gas. So its volume change from the initial to the final, and will keep the same amount of energy, and number of particles will be constant. Okay. So now let's look what happened with our entropy. Okay. So and K we can put outside. N is the same, it doesn't change. And here we get a logarithm of, and we just plug in here V final times 1 over N 4m pu over 3h square n in the power of 3 half plus 5/2 minus logarithm of V initial 1 over n 4m pi u over 3h square n in the power of 3 half minus 5/2. Okay. Guys, what could we do with these logarithms? I will skip it out because I write it down. What is the logarithm of, we can see here, V final, yes, times this, I don't know, blah, blah, blah. I'll write it like that. Yeah, it could be written as a logarithm of V final plus logarithm of this blah, 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 yeah? And here's the same here, logarithm of V initial and this one, yeah? So you can see that 5 half will be cancelled, these parts will be cancelled, and we'll just get nk logarithm of V final, and here logarithm of V initials, and we can write it down as V final over V initial. Does that make sense? So it's become very nice situation. So we get the changes of entropy when U and N fixed. And this is example of isothermal expansion. Yeah. So we have isothermal expansion. So when T is fixed, in this case, we can say that U is fixed. It's a simple example of isothermal expansion, as this is a nice formula for that. Okay. An example of that, we can have, for example, our chamber, and we have our gas here, and here's a vacuum, and then we have this hole, and from this hole, gas expands, yeah? Here we have a free expansion. Example. Okay, free expansion. In this case, we have a free expansion of a gas. Do we do work on it? No. Do we have a heat flow? No. Okay, so we have no change of energy. So we have no work, no heat flow, no change in energy. In this case, we can use the same formula which we just derived with U, and we can say that we know that delta U is equal Q plus work is equal to 0, no heat flow, no work. So in this case, we can use our formula, and in this case, we know that the change of entropy is equal to NK logarithm of the final over the initial. So entropy increase if volume increase, yeah? So what we have, entropy increases since volume increases. Okay. Now let's talk quickly about entropy of mixing. And next time we'll finish the last small bits about the reversibility and irreversibility of the ideal gas passages. Okay. So let's talk about entropy of mixing. Sorry. Okay. So we have two monatomic ideal gas. Okay. Two monatomic ideal gas. Okay. So we have gas here A, and we have here gas B. And let's just for simplicity may say that there is a same amount of gas molecules, the energy is the same, and volumes originally is the same. And what happened, we have the separation between them, and then we move the separation. So they are separated, and then mixed. And we'll look what will happen after they mixed, okay? So what happened if we mix, so we have gas A and gas B, and we remove the barrier. What will happen with gas A? Will it want to be in its 1/2 area? No. I could see that Miguel said no. It will want to go expand and occupy the whole volume. The same with volume B, it will want to expand and take the whole volume, yeah? So they both want to expand and take the whole volume. So let's look what happened with entropy change of the gas A. It will want to expand. So gas will expand, yeah, expand to full volume. So if you change the entropy of the gas A is equal to nk logarithm of V final or V initial, which is equal to nk logarithm of 2. And what is the entropy of B? Entropy of B is the same, yeah? Because we are saying that for simplicity it's the same story. So total change of the entropy is equal to change of entropy of A plus and change of entropy of B, which is equal to 2nk logarithm of 2. Okay? So this is interval of mixing for two different gases. Entropy of mixing two different gases. So now, will it work for two same gases?
Did you say two same gases?
Mm-hmm.
I don't think I would.
Why?
Since they are the same gas, they wouldn't mix.
I mean, even if they mix, they sort of stay in the same state. You're absolutely right. Yeah. So if you have they're in equilibrium, the same amount of it, there is no change of energy should flow. You're absolutely right. So now let's look if we have two same gases. Okay. So in this case, and we'll show it does not work. Yeah. So let's look at it. If we have same gases and we look in entropy, we look on S final minus S initial. S final, what happened when we have it here? We have a 2n gases, yeah, K, and we use the formula for gas logarithm of 2V, 2n, 4m, P, 2u, 3h squared, 2n, 3 half plus 5 half minus 2 times nk logarithm Vn 4 m pi u over 3h squared n in the power 3 half plus 5 half. And you can see that here all our 2's are cancelled, yeah? And you can see that the equation are identical from the top and the bottom, final minus initial, and it's equal to 0. So in our case, when we have expansion of the same gas, our number of particles increase from n to 2n, our volume increase from volume to 2 volume, and our energy from U to U. In this case, for the same gases, same gas, we get 0. So it is very important to have an account for indistinguishability of a gas molecules, yeah? And we use 1 over n factorial when we derive the equation. so it's, and if we have a distinguishable gases, in this case, it's, you can see the results will be totally different. Yeah. So if we have a same gas, if we put the entropy and we try to separate it, nothing will happen. And it also makes sense, and it's called Gibbs paradox. So so I just want to finish this thought for you guys. So if so why we want to make sure, why one gas have indistinguishable particles? Because if we put a sort of barrier between them, or we're not putting barrier, nothing will really change. Yes. And if they will be distinguishable, in this case order will change. And if we're putting the some kind of barrier between them and then remove the barrier, in this case we should somehow create the extra entropy, and then this is a paradox which calls the Gibbs paradox. And Gibbs paradox, just as a quick summary, and we'll just move on, and it's the end of the lecture. Gibbs paradox take into account that same particles must be indistinguishable. Okay. Otherwise, if we're putting the, as you can see, if we mix it, two particles, if they will be separate, in this case, our entropy will increase. Yeah. Here we have two gases where they were two different ones, and when we mix together, entropy increase. And here, if we have two same gases mixing together, entropy will be the same. So it implies if we have a system and we'll just put a barrier between two gases or the same gas, and if the, then to me, I feel like I'm going in a circle about this Gibbs paradox. Is it clear, or you want me, or it's not fully clear? Okay, good. In this case, I will not go in a circle. So Gibbs paradox saying that particle must be indistinguishable. Otherwise, we will. Otherwise, let me just write this one down to make it clear. Otherwise, by putting partition between partition, just putting partition, entropy will decrease more than twice, which doesn't make sense. Okay, if they were not distinguishable. Okay, I'm done, guys. So next time we'll talk about quickly reversible in the irreversible process, and we move to chapter 3. Okay.
Thank you very much.
Questions, guys? If you have anything else, you are welcome to stay. Questions?
I did have a question for the homework.
Sure.
I think it's
here, and other people would love to hear it as well. And
okay. It's 2.8 part C, and it's
let me open out. I don't remember it by heart.
Okay.
2.8 part C. Okay. Okay.
So my question is, I guess it's, so to find the probability, we have to find the multiplicity. Oh wait, never mind. I think
so find the probability. You need to find the multiplicity of one particular state divided by multiplicity of all possible states.
So let me check. I think it's part D actually. Let me just check
Part
my
D, okay.
notes.
Yeah, part D was what is the probability of finding exactly half of the energy in solid A? And we're using the multiplicity again to, I guess, just find the probability of multiplicity.
So you have a question about D or C?
D. So my
Okay.
question is, would you have to take into account the multiplicity of solid B here when finding the probability?
Yes, you need to have a multiplicity of both of them.
Why? I really don't see why.
Because you're looking in the system, and as the system has A and B, yeah.
Right.
So you are not talking about what is they interconnected together, yeah.
Let me read the problem really quickly.
Sure.
Sister.
So the question is, find the multiplicity of macrostate with half of the energy in each solid, yeah? So you need to find what is multiplicity of having half of the energy in A and half of the energy in B, yeah? So you want to find how many ways you can arrange A and B.
Right.
And then you find that what is the total of them, total multiplicity. For this particular state. So it's multiplicity of A times multiplicity of B. And from there you can find probability. I'm not sure, is it clear or not? You're not sure?
I mean the math is clear. Like I'm pretty sure the multiplicity for A for half states Q equals 10 is going to be the same for multiplicity of B.
Yeah.
What I don't understand is why. So for probability, it's just I thought it was just multiplicity A over the total multiplicity, but
Yes.
here you're doing A and B over the total, and I just don't understand why it's
same for all other ones as well. The multiplicity of macroscales of all energy in one solid, it's exactly the same thing. You always need to it's like they're together as a system. So in both of the cases, you need to have multiplicity of A times multiplicity of B.
Is that because we're going to have half energy?
Sorry? Arthur, I couldn't hear you.
Is that because we're going to have half of the units of energy in solid A and then half of it
exactly
in B?
Yes, and there is with that it implies there is still different way how B could rearrange its energy.
Because we're taking into consideration two Einstein solids, right? A and B.
Yes.
And the energy could be half in A, meaning the other half would be in B, correct?
Yes. Yes.
Okay.
Yes. I guess that's your question. I got your interpretation. So it's not like we give only half an energy. So we have the same energy and we just redistribute it. If you're saying that half energy in A, in this case, another half energy in B.
Oh, okay. I guess it's the wording of the question then.
Let's reread again how the 2.8, yeah?
Part E, I didn't answer. I didn't really
grasp. What is finding exactly half the energy? I see. What's the yes, I see your problem, Michael. What's the probability of finding half of energy in solid A? But here, I need to think, why do I need to care about B? Because they are system of two solids. They are together.
Right.
Yeah, and I see why it's a question, which implies that the same in the questions C, you should be careful. What is the probability of finding all energy in solid A? We still have to take account of probability of B, but in B it is easy. If there is no energy.
Right?
Sorry?
Yeah.
It's just one.
Yes, right? Exactly. because there is no energy. It's only one state. Nobody get anything.
Okay.
And how to find the all possibility? In this case, you counted all of them together for all energies. Yeah. 20
Yeah.
out. Mm-hmm. You have a question about E. Yeah.
Yeah, I didn't really understand E.
Let me read. Mm,
Is it just similar to how we were talking about entropy of how
let me just read
Yeah.
and see what I did here. Okay. I don't remember it by heart. You understand it? Just give me 1 second.
No, you're the professor. We expect you to know this by heart.
I mean, I know it by heart, but I still need to read the answers.
I'm just kidding. No way do I expect that.
Um,
Thank you, Professor.
bye. So I could tell you the answer. I'm not sure. I'll try to guide you to this answer. How about that? Okay. And let's me unpin this one so you don't need a piece of paper here. Okay. So still okay. So to answer these questions, let's look into cases where our system wants to be.
Balanced.
Balance, yeah. So this is the places when it wants to be. What happened if it's unbalanced? Let's take another example. Could give me extreme when it's not balanced.
When the extreme would be if you would have them unbalanced in like case B or case C, where you have half of the energy in solid A. No, when you would have all of the energy in solid A.
Yes. So if you have situation when all energy in one solid, it's unbalanced, and so you have a situation. And what happens if you let it go in time?
It will eventually disperse into both A and B.
Okay. So we have this direction. Could it go from to the situation back to C?
So that I so once we have the energy in both A and B,
Could we go back situation when it's all in A?
I wanted to say yes.
But the chances are.
Oh, okay. So that's what I was trying to relate to the entropy. I just didn't know how to word it within the realm of what we're doing here. So once it would be very difficult for all of it, as we saw, the number for it to be all in A is almost impossible.
So is this process, let's read the question, is it, under what circumstances would the system exhibit an irreversible process? Which will this process will be reversible?
And which process will it be reversible?
Is it irreversible or it's reversible, this process?
So for processes that would be reversible, you would have it when you have I'm sorry, I'm drawing a blank. I'm kind of confused a little bit.
So reversible process, if you're in equilibrium, you slightly move away from equilibrium and it wants to go back to equilibrium.
Okay, so when you start with half of the energy in both of them, in both A and B, and then you move it to like some other position.
Yeah, and it wants to go back. Now, what if we are in a situation when all in A?
Okay, I
We
see.
go back to this stage. Is it
I
reversible?
so what's important is state A, or sorry, state one and then state two. Like pretty much acknowledging if state one was all of the energy in A, and then it does whatever it does, say it splits into A and B, it would be irreversible then to go back to A.
Exactly. So
Okay.
I mean, there is a still tiny probability, yeah. So it's almost irreversible, yeah.
Okay.
The
Okay.
still probability, but chances pretty much is irreversible, yeah.
Okay. So that's the clear line I want, because like I know the number is still there. I just didn't know if we consider a very, very small number impossible or not. But I'll
So
take.
so it's pretty much irreversible, but sometimes, occasionally, in the chance very, very tiny, that could happen. It could be reversible.
Okay. Cool. That helps out a lot then.
Okay, good.
Okay.
Okay.
I'm good at
Other
least.
questions, guys? Ricardo?
Oh no, I'm just listening right now.
Linda?